Welcome to Talkcast, episode 206, if you're an audio-only listener, where I'm coming to you from Eastern Europe. And as I make my way from Hungary, where I am right now in Budapest, through to Romania and finally on to Bulgaria, I'm going to be passing through the, well, among other things, recent communist history of the region and enjoying also some of the more ancient history of the region. I didn't realise there were such well-preserved Roman ruins around here. Did you know that? If so, well done to you. I wasn't aware. There's a place in Bulgaria called Plovdiv, which looks absolutely astonishing. I haven't made it there yet, but hopefully I'll be recording some content from there and I'll bring you something from there in a few weeks. So of course it's only appropriate I show you just a few of the images and videos I've captured so far, which in the words of Julian Barbour, quote, reek of time, end quote. So this is a slightly different episode already. As you can tell, not only is this episode number 3 in my ongoing series about time, a series, if you've been listening so far, is a breakdown of the central themes of chapter 11 of The Fabric of Reality by David Deutsch, which is titled Time, the First Quantum Concept. This chapter is, perhaps more than most, if feedback to me is anything to go by, one of the most challenging and subtle chapters of the book, or indeed any of David's books. Many people have attempted to explain what time is over many years, and there seems to be no easy way to get across what our best explanations say about it. So today, I'm calling in the big guns to help me. So although this is indeed episode 3 of my series on time, it is also a bit of an interlude, I suppose. I am speaking today with Sam Kuypers, Dr. Sam Kuypers, we should say. Sam is a physicist who knows, I dare say, as much as any person on the planet right now about this concept we call time, what it is not, what according to our best current theories it happens to be, and perhaps most importantly, what he and some others are working on right now at the very edge of our knowledge when it comes to the deepest foundations of physics, the nature of reality as we best understand it. Sam is right there doing the hard, or the fun, work of finding out about what exists and what it does. I've been fortunate to know Sam for many years, as he is also one of those very rare physicists who happens to be an expert in epistemology. So Sam has studied Popper and he's got a deep understanding of what has come to be called critical rationalism and the history of the Enlightenment. And although today we will be largely focused on the theme of my ongoing series here right now, which is time, I did want to touch on facets of broader topics in physics and the Enlightenment because Sam is so knowledgeable, fascinating, and interesting to talk to about these things. Now, I don't want to put any pressure on Sam, and Sam, forgive me if any of this is awkward to hear, but as far as people go that are working at the deepest foundations of physics, among the deepest possible fields to make progress in full stop, he is a rising star. Sam began his studies at the University of Amsterdam in the Netherlands, where he earned a bachelor's degree before going straight on to a master's in theoretical physics. I met Sam just as he was finishing up that degree and waiting to be accepted into what is known as the DPhil program at Oxford University. DPhil, short for Doctor of Philosophy, or their version of the PhD. And I guess most people agree that the DPhil is really the higher degree. It's the bigger and tougher, more bulky brother of the PhD. The PhD, of course, being a degree which might have lost some of its sheen over the years. Every second person seems to be a PhD. Many people pejoratively say the PhD stands for piled higher and deeper. I'm not aware of any such pejorative jokes about the DPhil, but the DPhil in physics at Oxford, which Sam was awarded, I think only as recently as just last year in 2023, is universally regarded as one of the toughest and most prestigious qualifications in physics in the world. A hard degree program to get into, a lot of work to get through at one of the world's leading scientific institutions, or at least one of the world's leading scientific institutions. Sam now works in theoretical physics in Montreal, Canada, and we talk a little bit about that today, and he remains a colleague of David Deutsch, with whom he has authored papers, and some of which we're also going to talk about today. So hopefully you'll enjoy today's episode. The remainder of the audio is not as bad and echoey as what this introduction is. hopefully you'll enjoy my conversation with the great Sam Kuypers. Welcome to my third only ever guest, Sam Kuypers. I wanted to have you on because I've been talking about time and that part of the fabric of reality that is devoted to time, and I really needed an expert. And I thought to myself, well, I've been jokingly referring to you as Time Lord Sam Kuypers because you've written an important paper on the nature of quantum time. And what you do at the very beginning of that paper is to provide a nice overview of various perspectives of time that physicists have had over time. Now, I could have asked you on and interviewed you much earlier than this, but I thought that this particular topic would give us something central to focus on. Time as a physical quantity can serve as one of the themes of our chat today, but I'm also interested, and we'll come to, your take on the Enlightenment as well. And we might get to some other topics. I know that many in my audience are absolutely not professional scientists and they're not in academia and might be unsure exactly what any of this stuff about time, why it's interesting or what the point is. But before we get there, I just wanted to talk to you about becoming a theoretical physicist and what a theoretical physicist does day to day. Can you tell me a little bit about how is being a professional scientist that works in theory different to just about any other job that people do? What does your day-to-day involve?
Hey Brett, thanks so much for inviting me on the podcast. I'm a fan, I listen to it all the time, and it's very nice to be on here. Yeah, what does my day-to-day look like? Well, mainly I am thinking about very, abstract problems in scientific theories and then writing papers about them. So for the majority of the time, I'm either doing mathematics or I'm busy writing up mathematical results in a way that people can understand them. Usually work from home, so I'll just, I'll have a little bit of breakfast and then get to work writing up some stuff. And it's, as opposed to the fact that it's a little bit like, I guess, being an author or being a painter in the sense that you have a project that is really self-guided. Like, if I'm not an experimentalist, if you're an experimentalist, I think you need to work together with the team much more closely than I typically have to. So you have a set of things that you want to solve, some conceptual issues, and there is a lot of responsibility just on you for solving them. So, I'm currently working on some papers, and I just know that these papers, I and my colleagues have to write them. If we don't, it's somehow, it's not going to happen. It's hard to pinpoint the exact thing I'm trying to say here, but it's if you can't find a solution to these very niche problems in scientific theories, then there's this sense in which you feel like other people just might not.
It's an extremely creative exercise. You have to do the thing that no one else is going to do, as you've just explained. There's a misconception out there among anyone who's not involved in the sciences, who unfortunately went through the schooling system and were taught, well, here's the science in the book, and perhaps if they do high school physics, here are the laws, and then you can derive the predictions, and so therefore there's no creativity left. In fact, even physicists themselves at the turn of last century almost thought this kind of thing. Wasn't it lucky that Isaac Newton had discovered the system of the universe once and for all? And so therefore the only thing left to do was to work, I think it was in Eddington's words, to work in the 15th decimal place. So
Right.
What you're saying here is that there are just so many unknowns that you have freedom of a kind that is similar to the visual artist or to the sculptor. It's not complete freedom. You are constrained by what reality is going to dictate ultimately, but the possibilities for what direction you might want to go in is completely open to you. And you've just said there that if you don't do this, if you don't write the paper that you're going to write, because there is such a wide variety of things that physicists could do, some things will never get written, or at least not written for a long time, and can severely slow progress. Which brings me to what you might be working on now. I remember we first met all the way back, I think it was in about 2017, and I came over to
I was working at the time and I came to Amsterdam, and you generously showed me around Amsterdam in 2018. And then 6 months later, I was back, but you weren't in Amsterdam, and we both found ourselves in London. I think at this time you were then enrolled in your DPhil program at Oxford University. What took you to Oxford University? Of all the places that you could have gone to, was there a particular thing that drew you there? Was there a certain interest that you had that people over in Oxford were working on? Why there? Why not the United States? Why not remain somewhere in the Netherlands, which has a deep history of fundamental physics as well?
Well, I was interested in the foundations of quantum theory, and specifically in the work by David Deutsch, my colleague, and Chiara Mileto as well, Vlatko Vedral. And the ideal place to go seemed to be where they were working, which was in Oxford. So I had the opportunity, luckily, to meet them before then. And it just seemed like a place where the kinds of things that I was interested in were being researched. So, for example, in the Netherlands, one of the things that was a hot topic was string theory. I've not been very interested in string theory for whatever reason, although, I'm glad people are working on it. But it's the kind of things that I cared about seem to be researched in Oxford. So these are things like, there's philosophy of physics, which is a whole department there, and foundations of quantum theory, quantum information theory, many worlds, so interpretations of quantum theory. These are all topics that are extensively researched there. I was also interested in constructive theory, which again is not really done anywhere else. You can't really do constructive theory anywhere else. And yeah, these are all things which I thought were interesting. Also, Oxford is an interesting place for other reasons as well. So beautiful university, beautiful history, and I found myself drawn there. So yeah, for those reasons, I applied there and did my DPhil there. I was lucky enough to be able to do my DPhil in the group of Vlatko Vedral.
And what, well, I happen to have been someone who's read through your PhD thesis. Can you give us an overview? It's a big ask to do that in a podcast, but perhaps just a paragraph, an abstract form idea for the layperson about what it was you spent those years looking into, and ultimately what your PhD thesis was about.
So the main thing I was interested in was many worlds, is the Everettian quantum theory, as I think we should call it, really, which is the view that quantum theory describes a world that's constantly branching into what is sometimes called universes, separate universes, because that just seemed like such a counterintuitive worldview. I remember reading Fabric of Reality. I remember reading Fabric of Reality and thinking that I was basically on board with everything in the book, except for the bit about Everett, except for the bit about many worlds, and then ended up reading Everett's thesis to really convince myself that it was in fact true, just because I thought I'm supposed to be becoming a physicist. I read the book during my bachelor's degree, and I thought I should know about this. And it's so contentious what's being said here, in the sense that it's so contentious isn't the right word. It's so controversial what's being said in Fabric of Reality, but the argument seems so solid. So maybe if I can see the actual mathematics, it's right, or I can criticize it more thoroughly. And ended up reading Everett's thesis, and I thought, yeah, this just is true, but no one has ever told me it's true, except for David Deutsch, who wrote Fabric of Reality in the book. But other than that, it wasn't really a topic I ever encountered during my education. And I thought, well, the fact that this is so counterintuitive, the fact that this is so deep and makes sense of so many things which, before understanding it, hindered me, it should be researched. And that's what I ended up doing during my DPhil, really. There's several other topics which they have as their overarching theme that we should take quantum theory seriously as our deepest explanation, which is why we can, for example, apply quantum theory to things like time, that we were going to talk about, space-time as well, and just other topics which it doesn't really, like, all these other topics that I'm interested in wouldn't really make sense to think about from a quantum theoretic point of view if you're not also interested in Everett, or if you're not also interested in taking quantum theory seriously, I would say, in that regard. I mean, there are people who are not Everettians who are interested in, for example, the quantum theory of time, but as an Everettian, it is more coherent somehow.
Yeah, that mirrors, and I've told the story many times before, it seems like we had a similar experience. I was going through undergraduate, going to the lectures, being told the instrumentalist view, here's how you solve the equations, here's what the experiments say. We don't really understand what the experiments say, but that's okay. Wave-particle duality solves all of this. And so it wasn't until, I read that chapter 2, Shadows of the Fabric of Reality, then the scales fell from my eyes and I thought, aha, here's someone who's talking sense. And these days I'm a hand waver, so I'm sort of doing this quite a lot on the podcast and talking about the details of aspects of the theory that I understand, but you're the real deal. You don't need to wave your hands around. And so we're going to get into we might get into it right now, about aspects of the theory that are on the very edge of what we know, and you're pushing the frontier forward here. And so, well, let's go to one of your papers that you wrote most recently on Q numbers and C numbers and the calculus of Q numbers. We won't get to the calculus of Q numbers, but let's start right at the beginning, as you do in your paper, this quantum theory of time, and to clarify perhaps some of the historic thinking about time. Now, feel free to go wider than the way in which I set this question up, but you don't arbitrarily begin with Newton, because Newton himself famously wrote in the Principia, and I'll quote Newton here, and I've quoted him before in the previous episodes on time that I've done, absolute true and mathematical time of itself and from its nature flows equably without relation to anything external, and by another name is called duration. Relative, apparent, and common time is some sensible and external, whether accurate or unequable, measure of duration by the means of motion, which is commonly used instead of true time, such as an hour, a day, a month, or a year. End quote from Newton. So there we've got Newton's view, and it evokes this notion of something like a clock external to the physical world, and certainly unaffected by any goings-on in the physical world. There's just this universal time. The same clock ticks outside of the world for everyone, keeping track of time. Now, before we get to the quantum theory of time, let's take a step back and, keeping in mind, I think, what would be the common person on the street's idea of time, which is what Newton has just given us, this inexorable ticking outside of the universe, keeping track of time throughout the universe. It's deeply flawed for many reasons, but it was Einstein, I think, who perhaps was one of the first to challenge this notion of the universal time permeating the entirety of space. What's wrong with assuming there's this single clicking clock that it is keeping track of time for everyone, everywhere, all the time, as Newton implies, or as the person on the street might think?
Yes, so one of the things that is unclear from Newton's description is how do we measure this time, because the only thing we really measure are other physical systems. Like, if I want to measure time, well, I have a watch and I can see the time on the watch, but the watch is, in what sense is the watch keeping track of actual Newtonian time, of absolute time? Because it is the relative motion. It's like I can observe some motion that's happening relative to me, which is that true absolute time? And the thought experiment which I like to kind of distinguish these two visions of time is, as I put it in my paper as well, is imagine you have the universe, everything in the universe, including us, all the clocks in the universe and everything that exists. We don't need to go into quantum physics or anything. We can consider this to be a completely classical universe for simplicity. It still works. And then everything freezes in the universe for some duration, maybe 1,000 years, maybe 1,000,000 years, something like that. And then the question is, okay, well, things freeze, so everything is suddenly stationary relative to this absolute time. Absolute time keeps ticking away as usual. And then things unfreeze, and you ask yourself, could we have ever detected anything having changed in that way? Like, could anything have noticed that these thousands, millions of years of the freeze happened? And the answer is obviously no, because everything that could detect it, all the clocks and all the timers and all of those things, were stationary, and they, by definition, were stationary during the freeze, so they could not have registered that it happened. So that already hints that this Newtonian time isn't necessarily the thing that we observe on clocks. The clocks tick only, in the thought experiment, they don't tick, so they're not registering absolute time. But they're the only thing we have access to. So somehow there's this ambiguity in time in the usual way of viewing things that is kind of seems almost unnecessary. A similar thought experiment is, imagine you live in a universe, well, it wouldn't really be a universe in which you could live, but imagine a universe in which there is no time, there is no change, rather. If nothing changes, is there still time? In Newton's view, there would be time. Time would be ticking away, and nothing would change. And you could say, well, if nothing ever changes, then couldn't we just say that there is no time? Because it's clearly not an abstraction that's useful or necessary. Yes, so one of the things that is unclear from Newton's description is how do we measure this time? Because the only thing we really measure are other physical systems. Like, if I want to measure time, well, I have a watch, and I can see the time on the watch. But the watch is, in what sense is the watch keeping track of actual Newtonian time, of absolute time? Because it is the relative motion. It's like I can observe some motion that's happening relative to me, which is that true absolute time? And the thought experiment which I like to kind of distinguish these two visions of time is, as I put it in my paper as well, is imagine you have the universe, everything in the universe, including us, all the clocks in the universe and everything that exists. We don't need to go into quantum physics or anything. We can consider this to be a completely classical universe for simplicity. It still works. And then everything freezes in the universe for some duration, maybe 1,000 years, maybe 1,000,000 years, something like that. And then the question is, okay, well, things freeze, so everything is suddenly stationary relative to this absolute time. Absolute time keeps ticking away as usual. And then things unfreeze, and you ask yourself, could we have ever detected anything having changed in that way? Like, could anything have noticed that these thousands, millions of years of the freeze happened? And the answer is obviously no, because everything that could detect it, all the clocks and all the timers and all of those things, were stationary, and they, by definition, were stationary during the freeze, so they could not have registered that it happened. So that already hints that this Newtonian time isn't necessarily the thing that we observe on clocks. The clocks tick only, in the thought experiment, they don't tick, so they're not registering absolute time. But they're the only thing we have access to. So somehow there's this ambiguity in time in the usual way of viewing things that is kind of seems almost unnecessary. A similar thought experiment is, imagine you live in a universe, well, it wouldn't really be a universe in which you could live, but imagine a universe in which there is no time, there is no change, rather. If nothing changes, is there still time? In Newton's view, there would be time. Time would be ticking away, and nothing would change. And you could say, well, if nothing ever changes, then couldn't we just say that there is no time? Because it's clearly not an abstraction that's useful or necessary. And that's kind of where the two views start to really conflict with each other. Because Newton would have to say, no, absolute time is a thing which is always there. It is not influenced by anything happening in the physical universe. It's like a stage on which things happen, kind of like a ethereal stage that you can't really do anything to it, but events can unfold on the stage. But the stage is not itself a thing that you can really think about as being physical. It's just there. And yeah, so there is this problem in the usual way of regarding time, because you might think, and this is the way in which so-called timeless approaches to physics work, which exist both in quantum theory and in classical physics, you can just do away with this arbitrary time parameter that Newton introduced, this absolute time, and instead revert to the actual things that we can see in the universe. Like, I can see actual clocks, And there's lots of things in the universe that act as clocks. And time, relative to those physical clocks, has actual physical meaning. I can observe them, we can change relative to each other. And so one avenue of research is, why don't we try to restate the usual way of viewing time in terms of these actual physical attributes that exist in the universe. So a favorite example of mine, and I guess many people, is Barbour's construction. So Julian Barbour is a physicist in Oxford, and that's kind of where the two views start to really conflict with each other, because Newton would have to say, no, absolute time is a thing which is always there, it is not influenced by anything happening in the physical universe. It's like a stage on which things happen, kind of like a ethereal stage that you can't really do anything to it, but events can unfold on the stage. But the stage is not itself a thing that you can really think about as being physical, it's just there. Yeah, so there is this problem in the usual way of regarding time, because you might think, and this is the way in which so-called timeless approaches to physics work, which exist both in quantum theory and in classical physics, you can just do away with this arbitrary time parameter that Newton introduced, this absolute time, and instead revert to the actual things that we can see in the universe. Like I can see actual clocks, and there's lots of things in the universe that act as clocks. And time, relative to those physical clocks, has actual physical meaning. I can observe them, we can change relative to each other. So one avenue of research is, why don't we try to restate the usual way of viewing time in terms of these actual physical attributes that exist in the universe. So a favorite example of mine, and I guess many people, is Barbour's construction. So Julian Barbour is a physicist in Oxford, and
I've been quoting him recently on his famous line, "Time is in the instant is not in time," which I find is a parsimonious way of really getting to this idea that time is almost an emergent fiction, if you like, because if you have this idea of just a series of instants, you need never refer to this thing called time. But if you want to find time, then you can look. And I cannot find the documentary where he did this, but he holds up a picture of his own office and he says, the picture reeks of time. There is obviously change that must have happened before in order to lead to this state that we see now. And it's a mind-blowing idea that this thing that we are so familiar with, time, might just not be there in any way that we think that it is. That it seems to emerge. But yes, let's go on and tell me more about Julian.
I love the quote. Yeah, it's such a good quote. It reeks of time. And he holds up this picture. I forget, so you say it was of himself in the office. I always thought it was of himself outside. But anyway, yeah, it's of his former self. His picture of the past, obviously. As all pictures are, I suppose. And then, yeah, if you view that as another snapshot, then clearly something changed between when he took the picture and him now, and that's another. There's records. That's another thing. There's records of things that happened in the past. There's not records of things that happened in the future, and we have. And a record is a physical thing. It's a thing that we can look at and point at and say, well, that thing is a record. So. Yeah, those are all much more physical ways of viewing time. But Barbour, in his actual kind of mathematical constructions, the thing that he does is say, so it's quite classical. It's Newtonian. He says we can consider planets or massive objects in the universe, and they have positions relative to each other, which are obviously observable, and what if time is just a thing that emerges from the configurations of those massive objects? So that if they have some kind of unique configuration at every point in time, then you might as well say, well, there's just the configurations. We don't really need time. We can do away with time and instead say that the configurations are the thing which denote time. They are like the clock relative to which things evolve. So it's like the universe has a way of telling us what the time is within the universe. So it's not like we need a thing outside of the universe to tell us this is what the time is, which is really the Newtonian view. The Newtonian view is that we have everything that's happening in the universe, and then also additional to that, there is some kind of ethereal clock which is keeping track of time. Rather, in the timeless approaches, it is that you are within the universe, and you can track what the time is. You can look at physical attributes like configurations of planets and massive bodies, and then say, well, because of their configuration, we can say it's so and so late. And he has a short paper that is somewhat technical, which is very nice. I believe it's called The End of Time, but it could be wrong.
This idea that we could have a timeless view of the universe, I think at first blush many people would hear that and hear it make as much sense as saying we could have a spaceless view. If we take something like general relativity seriously, and we have this notion of space-time, and when I studied this, I just took it as read as, well, okay, space-time has a similar sort of physicality, a reality as what matter and energy do. You know, it's talked of as being a fabric, but of course, as soon as you think fabric, you think matter, and so, but it's not matter, but it does bend and stretch and warp, and famously, mass energy tells space-time how to bend, and space-time tells mass energy how to move, that kind of thing. And so we learn from that theory that space-time is the fundamental thing. And I was comfortable with that notion. I thought, well, okay, then space emerges out of that in some way, and time kind of emerges out of that. These are two emergent things from something deeper about reality, the space-time. In a similar way, the analogy I've been using recently, and it's probably a flawed one, would be the fundamental explanation of biology is neo-Darwinism, evolution by natural selection. At no point in investigating, evolution by natural selection do you find cats and dogs. Cats and dogs do appear, they emerge, and they're real, but they're not a fundamental part of the theory. Is this the way in which we might think of time in terms of general relativity? Or is that completely flawed? That time isn't a fundamental thing, but then nor would be space, and we can only speak of space-time. Or am I way off base now?
Yeah, no, I think that's right, that in a fundamental view, there is only space-time. So that's a way in which our current understanding of time is kind of limited. So, for example, my paper is about replacing Newtonian time, so this view of linear time as it exists in classical physics, with a more physical and also quantum mechanical view of the same thing, but it isn't yet space-time. So the problem that I consider is somewhat restricted in that it isn't. We don't yet have a proper theory of quantum space-time. We only have a quantum theory of time, which is in some sense quite modest, but beautiful. And but yeah, everything I agree with what you just said, that there is fundamentally there is only space-time in general relativity. There is space and there is time kind of as an emergent consequence of that. But you can't really think about one without thinking about the other if you're doing fundamental physics.
Yes. Okay, well, let's move into the quantum realm. Before we get to the quantum time, we do hear, and again, remember my audience are not in the main professional physicists, but that everyone who is interested in science as a casual observer will hear about a problem at the foundations of physics. On the one hand, we have quantum theory, an explanation of matter and energy, perhaps time, but let's leave that time aside for the moment. All the stuff that we can actually point to and we can pick up, quantum theory explains this. But you mentioned stage earlier as well. So these are the objects on the stage, but the stage itself, that's space and time. That's general relativity. And both seem to work well within their respective domains. Why can't we just leave it at that? Sam Kuypers, why aren't physicists satisfied with keeping these two explanations, which I hear work so very well, separate? What's wrong with that?
Yeah, I mean, so to some extent you can do that, but it's not a very good explanation if you dig a little bit deeper. For example, in general relativity, matter interacts with space-time. There is an interaction between the two. And we know from theorems by DeWitt that anything which interacts with a quantum system is also a quantum system. So that's the totalitarian property of quantum mechanics. And so that raises the question, like, is space-time a quantum system in that case? Because there seems to be an interaction. And in current theories of physics, space-time is completely classical. So it has, it's classical in the sense that there are real valued numbers that you can observe. Like if you write down a coordinate in space-time, if you write down a position and a particular time, you can do it using decimal numbers and fractions and things and real numbers generally. And that, according to quantum theory, that is that wouldn't be true if it were a quantum system. That it would work differently in that case. You would have to use Q numbers, as you said earlier. And maybe a more so if you know we're among Everettians, so we can talk Everett without having to worry. The way I always view it is, imagine that you have the Earth. The Earth is orbiting the Sun, obviously. Now, in other universes, there are very slight perturbations of the orbit of the Earth, and the Sun is also in a very slightly different position. So, in different universes, space-time is being bent differently by the Earth and the Sun. But so that means if you're in a different branch, space-time will look differently. But in our current understanding of space-time, there is no such thing as space-time being different in different branches. There is only how space-time looks in one branch, because it's classical. There are no branches. So that's the same way, really, of saying the thing I said before. Space-time doesn't admit that there are separate branches, but if we take quantum theory seriously, well, then the Earth and the Sun are quantum systems, and they can have slightly different positions in different branches, and that should affect space-time. But apparently, our best explanations can't really make sense of that. There's no way of making sense of what I just said using general relativity.
And so this is reminiscent of the way David Deutsch speaks in the beginning of Infinity about particles. Particles are not as simple as being point-like objects, but if I recall, he speaks of an electron as being more like an ink blot spread out throughout space. And so it doesn't have a sharp position at any given time. And the same might be true, correct me if I'm wrong, of something like the Sun. The Sun is much larger, but nonetheless, looked at fine enough scales, it will be spread out itself throughout space, which is going to affect something like planetary orbits. Now, at the moment, I guess, the technology is well beyond us to detect any subtle difference between this idea of the Sun being located at a particular place, being governed by the rules of general relativity, and the Sun being ever so slightly spread out like an ink blot, and therefore affecting the orbits of planets. Is that correct? Is that another way of looking at just what you've explained there?
Yeah, I think so. Yeah, I mean, so generally when systems get very large, they are susceptible to chaotic motion, and that is one way in which you can have different branches. So if systems are very susceptible to small changes, which they usually are the larger they get, I should be careful with my words here. Yes, I think so. So if a system is chaotic at any rate, then it is very susceptible to small changes, and that means that there will be lots of different versions of it in different branches of the multiverse. And we can just suppose that that is the case for the Sun. Maybe there was some event that made it have a very slightly different position in one branch rather than another, and then that's very possible. And then you would have the exact problem we just talked about. It could also be that, I mean, again, at a fundamental level, it is always a little bit spread out, as you were saying, however slight. It's never going to be, its position is never going to be exactly sharp. So, yeah, even if you don't assume what I just said, you always bump into this same problem that the sun is a quantum system and has quantum features that we can never fully get rid of. It's never completely classical. So the way it is affecting space-time depends on those features, but space-time doesn't seem aware that there are such features in the world. So we can't work with general relativity with those assumptions. General relativity just kind of breaks down when we start to talk about that kind of thing.
So I think we've established that there is a deep problem here to be solved, that we cannot simply rest on both theories working well in their domains. If we're realists and we want to understand the fundamental nature of reality, there has to be a way of either unifying these two in some way or finding another theory that is going to replace both at some point in the future. And you yourself are working on a part of this unification in your way with the quantum theory of time. And you've alluded to this already, and here we won't get too technical, but you talk about C numbers and Q numbers. We've thrown them around already. Well, can we refine that? What do we mean by a C number and what do we mean by a Q number?
Yes, so C numbers and Q numbers roughly mean they stand for classical and quantum numbers, although terminology was introduced by Dirac, and he apparently thought that they had slightly different meanings than that. He thought they were queer and commuting numbers. But anyway, so classical and quantum numbers. The classical numbers have the feature that they, for the purposes of the conversation, they're real numbers. So pi is a real number, e is a real number, 2 is a real number. These are things that have a definite value. And Q numbers do not have a definite value in general. They are numbers, if you want to be technical, they are matrix valued, but we don't have to go into more detail than that. Generally, they are numbers which do not have a definite value. So they, in some sense, they can represent things which have two different values at the same time. So if you're looking at a particle or a photon during some kind of interference experiment, then the photon is usually in two places at once. It's doing two different things at the same time. And these numbers are able to capture that. They're able to capture that the photon is not, for example, just taking path A or just taking path B, but is somehow taking both path A and path B at the same time. So numbers which can capture that are called Q numbers.
So let's then, that you've mentioned commutability or non-commutability, as the case may be in this case. And there are many windows on what is mysterious about quantum theory and how it manifests itself in the world to sort of challenge our intuitions about reality. For any who've got a casual understanding of classical physics, they'll know that, a quantity like momentum, you can speak of someone riding a bicycle with some momentum outside the post office, there's a position outside the post office, traveling at some velocity with their rider, there's your momentum. And there's a formula, momentum equals the mass times the velocity. And I can quote, in whatever order I like, the momentum first, 500 kilograms meters per second, and then the position outside the post office at x equals 0. It doesn't matter what order I give you these things in. That's classically, and that seems like common sense. This doesn't quite work, or quite might be underselling it, but this doesn't work in quantum theory. Can you explain what the problem there is and what the significance of this non-commutability is?
Yeah, so it's the thing which is a consequence of the non-commutability, the fact that you can't just measure one thing and then another and then reverse the measurements and it's always fine, is that certain things have to be non-sharp. So for example, if your position is sharp, if you have a sharp, well-defined position, then in quantum theory, which is our deepest explanation of the world, then your momentum cannot be sharp. And that's a consequence of the fact that these numbers do not commute with each other, that velocity and
by sharp, what we mean is a very small uncertainty. So we look at something like an electron, and when we say look, even that is problematic, we're shining a photon or something at this particular electron, and we're trying to say, here it is inside of this region of space inside of this box. But in doing so, in locating it inside of a box, we lose understanding, or we increase our uncertainty in something like its momentum.
Yes. Yeah, so the weird thing is that, when one thing is sharp, something else can't be. Not everything can be sharp simultaneously. Not everything can have a definite value at the same time. Some of the observables of a system have to be non-sharp. They have to be doing multiple things at the same time. They have to, for example, in the case of position and momentum, if you have a very, very well-defined position, then your momentum is in multiple states at the same time. You are in multiple, your momentum is spread out across the multiverse. So that's one of the weird things about quantum mechanics. It's not just that things don't always have a definite value, so that sometimes you are doing multiple things at the same time. Sometimes you are, as I said, taking path A and path B at the same time. It's that a system always has some observables which are doing multiple things at the same time. It can't not have observables that are... Sorry, should rephrase that. Some of its observables are always non-sharp.
And you begin your paper with talking about this non-commutability. How does it come to play in, if at all, into what you're unpacking and what you're unpacking? Perhaps we can take a step back.
Yeah.
You're talking about the Page-Wooters construction or Page-Wooters formalism of time. What is that? What was their significant discovery? Because it seems to me to be underappreciated. The popularizers of science out there do not seem to speak much about it. I've heard you talk about it. I've heard Chiara, I've heard David talk about it. But it seems to me that this is of central importance to progress in the foundations of physics as we understand at the moment. They are among the first to have brought time within the scope of quantum theory. Can you explain a little bit about what they did, what they achieved?
Yes, so to maybe connect this to the earlier story that we had, so in Newtonian physics and classical physics, time is this seemingly unphysical thing. It seems like when we talk about time, we don't really know exactly what we're talking about. We're talking about an ethereal clock somewhere that's not really clearly within the universe. And what we've just been saying is that quantum theory, maybe summarized, quantum theory says that the attributes of physical systems, or the observables of physical systems, have to be Q numbers. So they have to be these things which can be non-sharp, which can be doing multiple things at the same time, which maybe a more technical term for that would be they can be in superposition. And within quantum theory, Newtonian time becomes even stranger, because in quantum theory everything has to be a Q number. If you observe something, you're observing a Q number in quantum theory. And we observe physical systems like atoms to use them as clocks. But in the usual way of viewing time, you are measuring a Q number. So here Newton's C number time, so his real value time, is popping up in theories on fundamental physics, and it seems to be that is the thing which is the real time according to our theories. But then when we're in the lab and we're doing experiments on quantum systems, we're measuring these Q numbers. So the question becomes, how can it be that we measure Q numbers but to measure time, but time isn't a Q number? So we shouldn't be able to determine time from measuring quantum systems, and yet we do. That's my way of thinking about their construction. Page-Wooters came about it slightly differently, but ultimately that is the problem that they solved. It's the problem of how can it be that there are quantum systems in the world which have Q number observables, Q number valued observables, and how can it be that we use those to determine what the time is, which is not a Q number valued observable? And their solution is roughly that relative to what we usually think of as time, but this C number valued thing, the real value time, relative to which we are usually supposed to be evolving, that we're really stationary with respect to it. So they say let's assume that we're stationary with respect to that time, to Newtonian time, to the C number value time. Then can we still, in some sense, evolve? Can we still recover evolution and dynamics and all of that? But within the universe, so relative to some other system. So we have some system in the universe that we call a clock, which is a quantum system. Can we be evolving relative to a clock, even though, in another sense, the universe is completely stationary relative to the Newtonian time, the C number time? And their answer was yes. If you assume that there is a clock that you are entangled with, that's another somewhat technical term, you can assume that there's a quantum clock. So that is just, there is some quantum system, there's some atoms or whatever in the universe that exist and which are there, and you can use them as a clock, and relative to which you are evolving. So the atoms, you're evolving relative to this other system, and the other system is evolving relative to you, so that in some sense, if you add everything up, you're not evolving at all. I don't really know how to summarize that any more clearly than that. It's if you add up the evolution of both of these things, they're completely stationary. But if you look at one of them, then it's evolving relative to this other thing. So you are evolving relative to a clock, which is a quantum system. You can measure it and you can observe what time it is on the clock. But if you look at the totality of the system, of you and the clock, then you're stationary. And what's kind of happening is it's like a photo album. It's like the clock says it's 3 p.m. That's one state of the clock. And as the clock says it's 3 p.m., then you're doing a particular thing. So maybe it's, at 7 p.m. today we started to have this conversation, and then a little bit later there's another state of the clock that corresponds to us doing another thing. So half an hour later we're still having the conversation and chatting about time. And you can add all these things up, so you can kind of look, what's the clock doing, what am I doing, and if you add them all up, you somehow have, in some sense, a stationary world. We just have these snapshots of the world and things happening in the world, together with the clock that's labeling the moments at which these things are happening. But they add up in such a way that they're stationary. Like the snapshots are not really changing; they're just there. If you look at the photo album isn't. You can think about the photo album as not really undergoing any change. It already contains all the photos within it that it's going to store. And you can look at people getting older. If you can leaf through the photo album, you can see these people in the photo album are getting older. But it's not, I mean, you can also leaf back and then see that they were young at some point. And it's, if you look at the whole of it, there is no, in some sense, there is no time in the sense that the photo album is already there in full. Like you can get a sense of time in the sense that the photo albums tell you a story, but the photos are themselves not changing. They're just there. They're stationary pictures of the world.
That's the way that I've tried to explain it to myself recently in reading your work, going back to Page-Wooters. The word changing that you just used there. Nothing is changing, but there is change. So you look at the beginning of the photo album, you look at the end of the photo album, there has been change. But at no point will you see something changing. You can flick from one instant to the next and notice the change, but there's no additional motion over and above the physical processes that are going on inside of the universe. And as you eloquently put it, if we were to freeze the physical processes, there's no sense in which we've got some additional thing flowing that is kind of still going on, as if there's this fluid going through the universe, but everything else is just frozen there. There is no such fluid. But I think that notion of flow, as if things are being carried along by a river of some sort, and this is what time is the thing that you're doing away with, because there's no physical reason to invoke such a thing. And you're a physicist, Page-Wooters a physicist. They want to talk about what's physically happening, and what's physically happening is the motion or change of particles, of there's a vent, then there's a vent, there's a vent, but nothing is changing. There's no smooth, continuous, one might say, gradual flow of one moment to the next. It just is instants piled up one upon the other.
Yes. Yeah, that's a very nice way of putting it. Yeah, it's... Yeah, just as I said, the photos in the photo album are not undergoing any more change in our metaphor. They are just there. And the moments in the universe are just there. They themselves don't change. There's just a succession of them. And the succession of moments is what seemingly gives rise to time. But there is, in a fundamental sense, there is just moments. There's just snapshots of the world.
Now, I have two technical questions, then we'll get to some more fun questions. Well, I find these fun, but I think the audience might find them rather obtuse. Your advance in your paper was to take Page and Wooters and to introduce the Heisenberg picture to this, because we have these two ways of looking at quantum theory. So let's do our best, or I'll ask you to do your best, for the layperson, to try and explain these two visions of quantum theory, the Schrödinger picture and the Heisenberg picture. They're equivalent ultimately, but what's the difference?
Okay, so this is a point where I can't avoid being technical. So in the Heisenberg picture, is nice because you're dealing with observables that are changing in time, and which is something that we're very used to from classical physics. Like if you do classical physics, then you say, well, there's a particle, it has position, and the position is a function of time, and it's changing relative to that time. And so the position, there's momentum, all these quantities which are time dependent, and you can get expressions for what the position of a particle should be at some later time in terms of its position and momentum at an initial time. And that is basically how the Heisenberg picture functions in quantum physics. So the Heisenberg picture tells you there's these observables, they are position, momentum, or whatever. There's specific examples of them, but they can be different as well. And they are functions of time, and we can express these Q number valued observables, so again, these are Q numbers, in terms of the Q numbers at some initial time. And it's a nice view of quantum physics. It's the more fundamental one, in the sense that, well, for one thing, it makes a theory more continuous with classical physics. It makes it clearer what's actually going on, and makes it easier for us to carry over ideas that we have established in classical physics and use them in quantum physics. It is also nice because it's a local description, but that's maybe a discussion for another time.
Well, no, let's just in a couple of sentences, just explain, what do you mean by local?
I mean that if you have two systems, so I have system A and system B, and I do something to system A, then in no way should system B be affected, neither in terms of things that can be observed or in terms of its actual factual situation. Its actual state should not be any different. And in the Heisenberg picture, that's very clearly the case. In the Heisenberg picture, what you do is you say there's observables of system A, or descriptors, as they're sometimes called, of system A, and observables of system B. And when you do something to system A, its observables change, and those of system B, which is isolated from system A, do not change. So you can do something to system A, and it doesn't actually affect anything that's happening to system B, even in exotic situations. So even when they're entangled with each other, this result still holds. That system B, its state is just unaffected by things that happen to system A.
And this preserves, for example, the prohibition on faster than light communication, that kind of thing.
Yeah, so in both the Schrödinger and the Heisenberg picture, that faster than light communication is not possible, because, of course, these are just two ways of describing the same theory. So the actual observable consequences should all be the same. The thing that people often worry about is that in the Schrödinger picture, it's not clear what it means for something to not be affected by another system. Like the description of systems A and B is not something that you can separate in the Schrödinger picture. So you have system A and you have system B, And in certain circumstances in the Schrödinger picture, you can't really separate out their descriptions from one another. So you seem to have to be committed to the idea that if you do something in system A, well then since its description is completely wrapped up in that of system B, you've in some sense also done something to system B. So in the Schrödinger picture, to also give a brief overview of that, you, instead of having these observables which change with time, the observables are stationary, and there is another thing called the state vector, which does change with time. And the state vector is this thing which generally you can't really decompose into things that represent system A and represent system B separately from each other in such a way that you can put it back together again, for example. So in many situations in the Schrödinger picture, there's only the total description of system A and B combined, but not either of them separate from the other. And then you get into weird ideas like, if they're entangled, well then maybe it really is the case that if I'm doing something to system A, then it does change system B, even though I can't observe that happening. But my description is telling me that something is happening to that system, because after all, they're not separable from each other.
So you couch your research in terms of what's known as the Everettian relative state explanation of quantum theory. Can you distinguish for me that idea, which is a proxy for the multiverse or for the many worlds, if you like, which can be misleading terms, from what I sometimes hear called unitary quantum theory? What is unitary quantum theory, and how is it to be distinguished from Everett?
Okay, so generally, people think that quantum theory works in two ways. You have something called unitary evolution, which is evolution as dictated by the Schrödinger equation or by some fundamental equation of motion. There's others like this, the Dirac equation as well, but all the fundamental equations are unitary, meaning that they have, for example, the property that they are reversible. So if something is going one way, then there's a unique way in which it can be time reversed. And then there seems to be a second way in which systems evolve, and that is non-unitarily during measurement. So you measure something, and then it seems to be the case that something happens which violates unitarity. The reason for this is somewhat straightforward. It's if you assume that something can take several values at once, then during measurement you only ever see one of them. So if something is in a superposition, you only see one of the measurement outcomes of a thing which is in superposition. Beforehand, you don't know which one. And the equations don't seem to tell you. So you end up seeing one particular result, which wasn't picked out by the dynamics, seemingly. So there seems to be a way of moving forward, but you can't really go back. It's not reversible. It's not a reversible operation. So during measurements, the universe seems to violate unitary or reversible dynamics. And the important thing here is that everyone believes that quantum theory describes a world which is at least evolving unitarily most of the time, and then not unitarily some of the time during measurements. What Everett really did was say, we don't really need this second process of measurement to be anything but unitary. We can actually give a unitary account of measurement, and therefore do away with this odd dichotomy of having to use different rules in very parochial situations. And so sometimes Everettian quantum theory is also described as unitary quantum theory, just because it takes seriously the idea that quantum systems only evolve unitarily. That's really, if you read Everett's thesis, this is how he describes it. He says there are these two processes, and the second one, the non-unitary one, is arbitrary and weird, and every time we try to explain why it's there, we have to invoke more arbitrary and weird stuff. Like, for example, there's the idea that maybe there's a separation between the quantum and classical worlds. Okay, where does that separation happen? Where, like, if we have 10 atoms, is that a classical system? So that if it measures something, can it measure things? Is it classical? Does it count as a classical measure? Maybe does it count if we have 50 atoms, if we have 100 atoms, if we have 200 atoms, 1,000, a million? Where is the cutoff between the quantum and the classical world? So it does away with all these weird distinctions. We can just say the world really is fully quantum, and there is really only unitary evolution, and the seeming non-unitary evolution is just the result of our particular vantage point. It's just that what's really going on fundamentally is that there is something unitary happening during measurement, which is that you branch into several versions of yourself. So there's one version of you that sees one measurement outcome, and then there's another version of you that sees another measurement outcome. And you have to be one of them. You're going to be one of these versions of you in the future. You will be one of them, and you can't see the other ones. So because of your vantage point, you can't see that the world is really larger than you are experiencing it as being. So then it seems like unitarity is violated because you just don't see the other versions of yourself during such experiments. And so that's why Everett is sometimes called unitary quantum theory, because it takes seriously this idea that really everything is just unitary evolution.
Quantum theory, a special dispensation is made for quantum theory in philosophy and throughout physics, which is bizarre and unusual. And anyone who comes to Everett is able to look back and go, isn't that a strange exception to the rule that we've made? It would be as if when Kepler first came up with his rules of planetary orbits, that there were people who would object on the basis of saying, well, we never see a planet at every single point around the orbit. The orbit is just a fictional path that doesn't really exist. There is no reality of these orbits. All you ever see is the orbit collapse to a position where you observe the planet at any given point in time. Of course, that would be ridiculous. We know that if the mathematics describes the orbit, that's where the planet is actually going to go. And in the same way, the Schrödinger equation taken seriously describes that, particles occupy multiple places simultaneously. Just take that as the explanation for why you see the particle in the one place that you do. Necessarily, you find yourself in one particular universe out of the uncountably infinite number of universes where it could have been. So let's tidy up with two sort of fun questions on time. The first one is, does time exist, Sam? What do you say to that?
So time doesn't exist in the sense that there is no absolute time. There is, in some sense, we live in a stationary universe, and we, just like with the previous example, we just don't see it from our vantage point. Our vantage point is such that we see change, and we can talk about change and talk about time as this emergent thing because of that. At a fundamental level, there is no time in the sense that there is only, to refer to the previous metaphor, there is only the photo album. The photo album doesn't change. It just contains all the photos that describe someone's life. And the universe just contains all of the events that are its history, but there is no change outside of that. So in a fundamental way, there isn't really time. There is only the events, the moments that exist.
Almost any science fiction writer who has ever written on the topic of time invokes time travel, which brings in black holes, wormholes, this kind of thing. So is time travel to the past possible? If not for the many worlds interpretation, we would have strict paradoxes, like if you prevent your grandparents from meeting, you'd never be able to jump into the time machine because you wouldn't have been born. But with the many worlds, other times are just special cases of other universes, although there is a prohibition on communicating with counterparts in other universes. But could we nevertheless, in principle, given what we know about physics at the moment, could we nevertheless have time travel into the past and take a high fidelity look at what's going on there, almost like visiting a zoo in a way?
Yeah, so I honestly do not know. I wrote a paper about this topic, and the paper is really showing that the paradoxes which you would think are there don't necessarily have to happen. The paper doesn't show that that there might not still be other problems. For example, I only show that some paradoxes don't happen. I don't show that paradoxes never happen. So in that sense, the paper is a bit open-ended. But there are good reasons for believing that time travel is possible. For example, we know from general relativity that there are places inside black holes, rotating black holes, where you apparently should be able to time travel. Again, if you take general relativity seriously in those situations, which there's no reason that we know of not to. So it seems very likely that time travel is possible. It seems that, at least in the case of things like the grandfather paradox, at least in the case of well-known paradoxes, so the paradox of going back and killing your own grandfather, which would then seemingly prevent yourself from being born and therefore from going back in time to kill him, that those things are not problematic because there are ways around them. As you said, because of many worlds, you can go back in time, and if you end up in another universe, then you don't actually influence your own past, or your own past is already written. You can influence the past of someone who is very similar to you and who shares a history with you up to the point where you time travel. So you're ruining the life of an alternative version of you by killing his grandfather, but you're not actually, I guess you're preventing yourself from an alternative version of you from being born by killing his grandfather, but you're not actually killing yourself, and so you avoid the paradox. But I wouldn't say that we have completely figured out this part of physics yet. It's still, there are still open problems. There's still problems which I think should be solved before we really understand what's going on there. And I don't know what's needed for that. Maybe maybe it would turn out that slight variations on theories that we already have would be enough. Maybe it turns out that we would really need something like quantum gravity to truly understand what's going on in these kinds of situations. But at any rate, we know that there are somewhat straightforward ways of avoiding the paradoxes, so that they are not a fundamental obstacle or a good criticism of the idea that we can't time travel.
One final question about physics for now. No, not specifically on physics, but more about how you got into the area. Physics is fashionable again right now, which is exciting. You know, the movies being made about it. People are singing its praises. You know, everyone from Elon Musk down through the ranks of the most wealthy. People seem to be understanding that breakthroughs at the fundamental level are what make the biggest changes. Now, sometimes I think many of the people who are espousing praise for physics might be off-centre just a little, because they might be thinking in reductionist terms, that everything just reduces to physics. But at least we do have a new resurgence in interest in physics. Now, you're not only working in physics, you're working in the deepest possible part of physics, at the foundations of physics. And that's what we've been talking about here today. I did say I'd come back to this. So were you in high school, sitting in science class or somewhere else, thinking, I want to work at the foundations of physics? Or was it more nebulous than that? You know, you liked physics but didn't exactly know how you'd get into it. What did your personal journey look like? Was there someone, or was there some books that inspired you? What helped you make the transition from, as many of us are, confused teenager, not sure what they're going to do, to someone now working alongside the likes of David Deutsch on the foundations of physics?
Yeah, so actually for the longest time I wanted to get into animation. I was really into art and drawing, and initially during high school I wanted to become an artist, or to become an animator. And at the same time I was always fascinated with physics, and I specifically, having conversations with my dad, who was into science, helped me was the kind of thing that was fun. I still vividly remember having like questions about the natural world that I would ask him, and be like, isn't it strange that this and that happens? Or he would explain, like, oh, do you know that there's a moment when you throw a ball, this fascinates me, that if you throw a ball in the air, there's going to be a moment when it's completely still. And I would go, how do you know that? That's a very strange claim to make. You go, well, it changes, its motion at some point, and then by virtue of it changing its motion continuously, there will be a point when it's stationary. It's not moving up or down, and it's like simple things like that were things that I always discussed with him, and eventually it got to the point where that became my main interest. So I would be doing mathematics on the side, and I was interested in electromagnetism in high school and things like that. And then at some point I decided that was the thing I wanted to study.
And the culture in the Netherlands is very much one that fosters an interest in science. And that gives me a sort of an awkward segue into the next topic I wanted to broach with you, which is about the Dutch Enlightenment. And you're the first one to have opened my eyes to, well, perhaps there is this antecedent Enlightenment that predates even what was going on in the United Kingdom. We're often told about two forms of the Enlightenment that are in tension, the British Enlightenment, or more precisely the Scottish Enlightenment, and the Continental Enlightenment, where both were recognising the primacy of the individual. But on the one hand, the British were saying, well, the individual has their inalienable rights just by virtue of them being a person. The continental version was, well, we need the prince or the leader to confer these individual rights upon people. And so, in some sense, they're deeply at odds with one another. Both of them sort of grew out of a tradition that was towards the end of the 16th, maybe 17th century, something like that. But of all the things to raise, I guess that my in here would be the Dutch East India Company was spreading itself across the world, was spreading trade across the world. It's probably not a beacon of capitalism as such, but hey, they were trading and they were innovating and they were bringing to the world difference, creativity. So take me to the genesis of the Dutch Enlightenment. How is it different to what was going on either in Britain or on the rest of the continent?
So the thing which the Dutch bring to the table, in my opinion, is something like the invention of liberalism. That the Brits, I remember reading the book by Daniel Hannan, How We Invented Freedom, where he argues that British democracy, that England invented freedom and democracy, something like that. It's the rough, if you want to have a nutshell summary of what the book is about, that's roughly what the book is about. And I remember thinking that was pretty persuasive at the time. And at some point, I switched and thought the thing that the Brits really brought to the table was stability. It was political stability. And the actual dynamism that comes with an Enlightenment, so with the British Enlightenment, the Scottish Enlightenment, that was not due to the Brits as such. So what I think really happened is that Britain had a very stable political system relative to other political systems. I mean, it was still horrendous in many ways. There were civil wars, there were kings who were betraying the country, but they had a parliament which, for example, the monarchy just couldn't get rid of. So whenever there were conflicts with Parliament, then it would happen that it was dispersed. It was Parliament would disappear, but then it would always come back. So it had a very strong tradition of there being a Parliament. But the actual dynamism and the actual idea that there's things like innovation, there's things like this critical attitude that you could have, and the scientific inquiry and things like that. I think those were mainly coming from the Netherlands. So during the 17th century, the Netherlands was in the Dutch Golden Age, which was a period when they were extremely productive and extremely innovative. And it is during this time that England had problems with its monarchy several times. So first there was Charles I, who was killed and replaced by his Lord Protector Cromwell. Then Parliament reinstated Charles II after the death of Cromwell. We really think his son replaced him for a while, and then Charles II was reinstated. And then came James II, and at some point Parliament said that this difficulty with the monarchy should be resolved. And at the same time, there is another Protestant nation, neighbor nation, which is facing similar difficulties with its neighbors. So there's the constant threat of Catholicism from Germany, from France, or from the German states, I should say. Germany was not then unified. And at some point, Parliament decided to invite the stadtholder of the Netherlands to come and replace James. And he did so. He successfully managed to overthrow James II in what's now known as the Glorious Revolution. And I think that was the moment at which the dynamic culture of the Netherlands was imported into England. So that not only were the difficulties with the monarchy resolved and causing Parliament to actually gain genuine stability, not just relative stability of always existing and coming back, but of actual genuine stability, but also of having this dynamic culture which was being imported and which really reshaped the whole of English society. For example, the English bank was modelled after its Dutch counterpart by Downing, and just life was very, very different after the Glorious Revolution and after the Dutch influence. So this is, they called it at the time, they were Going Dutch, which is also the title of a nice book by Lisa Jardine about this topic, about how the Dutch influenced the Brits. And I think that is, that's the more persuasive story to me. I can go into detail about the things which...
And so were the Dutch early pioneers on codifying things like freedom of expression, trade between people, were those things also early on during the Dutch Enlightenment?
Yeah, well, trade was a big thing. As you said, there was the East India Company, which was a state monopoly. Initially, there were several different trading companies which were then merged into one big one early on at the start of the Republic's existence. They were merged. But even so, the trade was the main engine of the economy. So they leveraged specialization in a way that maybe hadn't really happened before anywhere else in the world. I once spoke with David Friedman about this topic and asked him, so is it fair to say that the Dutch were the first country to really base its entire economy on international trade? And he said, yes, with the possible exception of certain Islamic countries that we just simply do not know if they have done the same thing. But as far as we know, that the Netherlands was the first, yes. So its economy was based on international trade. It had a very high standard. It was very tolerant. Many thinkers fled to the Netherlands and sought refuge there, like John Locke, René Descartes. They went to the Netherlands to live their lives there due to the environment of tolerance that the Republic provided. And so tolerance was important, trade was important, Protestantism was a thing which was, I think, brought all of this about in some sense. I mean, it wasn't, I should be careful here. The Netherlands came about due to it being a Protestant country that wanted to be Protestant in what was otherwise a Catholic state. So there was the 80-Year War, which is basically the War of Independence, where they gained these freedoms of religion, which were integral to the functioning of the Republic. So that is why tolerance was so important to the country. It's one of its founding principles almost.
It's difficult to underestimate the seismic shift that trade brought with it and the genuine innovation that trade is. Up until the point that a place like the Netherlands literally invented this notion of trade, the rule throughout the world was if some other community or tribe or nation had resources that you wanted, you didn't trade, you went to war and you just took. And so it takes some sophistication and some ideas about criticism and non-zero sum winning to recognize that you can actually, at the level of corporations as well as individuals, both win by trading. It's amazing it didn't happen sooner, but if it had have, we may be in a better position than what we are now. But someone had to be first. So thank goodness for for the Dutch.
Yeah, well, it's interesting that you say that, because even at the time it was unintuitive to people. Like the Brits were saying at the time, there's Lund, who was a MP. He said that the Dutch are making us slaves because we are exporting more. Sorry, we're importing more from the Dutch than we're exporting to them. So he was a mercantilist, and he
sounds like Donald Trump.
Yeah. So these theories clearly have a very long lifetime, yes, which is bizarre. But at the time you can almost forgive them. I mean, not quite, but you can almost forgive them because it was a new thing. There wasn't really a country like that. Yeah, you can almost imagine seeing a completely new kind of country come into existence, and there was some animosity from, for example, England, which is odd. It's odd to see. One of the things that fascinates me about the history is that England and the Netherlands were both Protestant nations, and you would think that they would be naturally friendly, and they weren't. There were several wars between the nations, even in the 17th century. So even some years before Parliament invited William III to come and be the new monarch, there were wars between the Netherlands and England. I guess that's partly due to the fact that, for example, Charles II started a war. He started one of the Anglo-Dutch wars, in which they stole or took, depending on who you are, I guess, New Netherlands, which is now New York, or New Netherlands is really larger than New York, but there was one colony that the Dutch had that they really cared about. They had lots of trading outposts. I'm kind of rambling a little bit, but they had lots of trading outposts where they didn't really treat the trading outposts like the Brits would treat their colonies. The Brits really treated their colonies like places that they would go to, and then they would teach people the language, and they would try and convert people to their way of life. And the Dutch never really did that, except in New Netherlands, which had as capital New Amsterdam, and which was taken by Britain during the Second Anglo-Dutch War. It's very strange to see this animosity between the countries, but also the way in which their cultures are so intertwined with one another.
Yes, and it's strange to see, as an Australian, to see how the animosity evolves into sort of friendly banter to some extent. Like, I remember as a child noticing that the British didn't like the French for reasons I couldn't quite get a handle on. It wasn't that there was great animus there, but there was a friendly rivalry. And then I remember I think it would have been my early 20s, watching this comedy movie, I don't know if you've seen it, Austin Powers. And Austin Powers is the takeoff of James Bond. And there's a line there where Austin Powers says at some point or other, he doesn't hate anyone. And then he looks at the camera and he says, except the Dutch. And I thought, why is this British fellow doesn't like the Dutch? And it wasn't until quite recently I figured out, there has been this long history of war and which has morphed now into just friendly digging at one another, I think, on either side of the English Channel kind of thing.
I mean, relations between the two nations are clearly very good, especially considering historical standards. And I remember, so during the Second Anglo-Dutch War, the Dutch had the so-called Raid on Chatham, where they burned down lots of ships of the Brits, of the English. I keep calling them Brits, but really it was England. And they took back with them the flagship, the Royal Charles, which is still on display in Amsterdam, at least the back of it is. And every now and then, apparently, they ship it back to England. And the story goes that every now and then they will message the incoming ship with, so sorry, who are you? And this is these are the Dutch, and we're here to show the Royal Charles again in Chatham. And they go, you again? Just for fun. But yeah, so it's clearly the history is still funny to people.
Yeah.
And it's very odd.
I'll finish up with a hobby horse of mine. As we record this, in fact, just before I began speaking to you, I noticed that once again, my favourite podcaster out there, Sam Harris, has released another podcast denying the reality of free will. I think free will's become a triggering term that means that the discussion around what is called free will sometimes needs reframing. It basically becomes like, well, do you believe in free will? And then you're defending yourself almost like you're defending a religious doctrine. Whereas what I'm often going on about on my podcast and elsewhere is that people are unique, and that demands an explanation of some kind. If I look out my window here right now, I can see in the environment, trees and birds, the ocean off into the distance. And I know that those things are shaped by purely natural forces. I can explain everything there in terms of, the physics or evolution by natural selection. But then also, anyone looks out their window and they say buildings and buses, roads and aircraft, and none of that can be explained in terms of, well, it's just the outworking of weathering and erosion and natural selection. You need to invoke people, and more than just people, you need to invoke something about people, choice, creativity, the inherently unpredictable, and that sets people apart in a truly fundamental way from everything else we know. And I want to know from you, because it seems to me this denial of free will, and I'm going to be controversial here, I think I just put it out on Twitter, it seems to be on a continuum with an anti-human impulse that pervades culture. It's a peculiar thing in our culture. I mean, there's always been anti-humanism, but at the moment there's everything from the practical kind of anti-humanism, namely that people are ruining or destroying the environment, and so we need to save the environment at the cost of people. So you need to make yourself more and more uncomfortable by using less and less energy or less and less resources. So there's that kind of humanism, which is annoying and in fact can become quite dangerous. The Extinction Rebellion people who, hold up traffic. But it is a continuum. There's all the way from that through to abstract musings, abstract philosophical musings over people have no more free will than like insects do. We're on a continuum of intelligence alongside the insects, the frogs, cats, chimpanzees, and we're the next dot on that graph. Now, the latest one, of course, is that we're just a large language model. We're just some sort of LLM, and maybe ChatGPT-7 will be a better person than any person that's out there now. I think this is almost a ubiquitous idea out there on Twitter at the moment. What are your thoughts on this? What is it about two things? The uniqueness of people, what is their place in this world, and what is driving this anti-humanism? Because at the moment we have two things operating which seem bizarre to me. A wonderful civilization that is flourishing with more creativity than we've ever had before, the uniqueness of people, and on the other, a response to this which is a deep anti-humanism of a kind that is unique in form, if not unique throughout all of time. We've always had people who've wanted to kill one another, but now we have a deep intellectual movement that is behind the people who don't like people.
The first question was, why are people special? What's special about people? And yeah, there are these ideas floating around that people are not special, that free will does not exist, that our place in the universe is not really indistinguishable from rocks, insects, things like that. They always strike me a bit as copes. For example, if you go to court, you can't really argue that you are as responsible as a rock is or anything like that. Like theories about responsibility. I mean, free will. We don't really have a proper theory of free will. I would think it is going to be deeply entwined with problem solving and with our ability to understand the universe, but we don't really have a proper theory of it. But the other views, the idea that there is no free will or there's nothing like that, are really weak. Like, for example, we need this idea of choice in courtrooms. We need to be able to say, could someone have done otherwise? Were they the cause of someone's death, or were people bystanders? Would the death have occurred anyway? People can make choices and be held responsible for those choices in law. That always strikes me as a little bit of a cope to say, well, this moral responsibility, which we clearly have, isn't actually there. I don't really see how we could argue that. And it is a very strange thing that we are as prosperous as we are now, while also being in a stage where anti-human ideas seem to be more popular than ever. I'm not sure if that's true, actually, but it's easy to say that, but it's really hard to quantify that. I mean, on the one hand, I wouldn't really know of any pro-human ideas that are very mainstream. On the other hand, there are lots of people like yourself and people who, for example, run the Human Progress website and Twitter account, and there's David Deutsch, there is Matt Ridley, lots of people who are pro-progress and are saying so. I've noticed that they are not diminishing in number. I've only seen them grow. There's still a minority of people. It's not mainstream yet, but yeah, it is heartening to see that. Same with Pinker. Pinker's books on progress are good. I don't agree with everything in them, but it's still heartening to see someone talk about progress so openly. Yeah, it is a weird mix of things. I don't know what the appeal is that people see in the anti-human ideas. It's clearly very compelling because lots of people just disappear down this rabbit hole thinking that people are the worst things that have ever existed. Like we will. I guess there's a kind of perverse moral pleasure that people take in, for example, saying, well, humans are like cancer or humans are like a disease, because it's feels edgy and hurtful, but also people presumably think it's true and that therefore it's legitimate to say things like that. So yeah, there's that element of it. Yeah, so there's a kind of perverse moral pleasure that people take in that. And very simple theories about the world do seem to imply this. I guess that's the more rational aspect. If you do not account for creativity in your worldview, then it really does seem like maybe people are not that great, because you're leaving out the main thing that makes people special. If you're not accounting for the fact that people can innovate, well then yeah, maybe we're going to have a famine, because the population is growing faster than their ability to provide food and produce food and distribute it. But all those theories don't work precisely because of creativity. It's precisely because of the fact that people can innovate and find new kinds of solutions that the theories of people like Malthus don't work. And in their defense, it is not a trivial thing to take into account. It's not really a thing that you can use to defend people now, because we know now why theories like that don't work. But the Steelman version of the argument would be that if you're leaving out creativity, it really does seem like maybe people are kind of doomed. But they're not. They're not actually doomed, because we have innovation and we have creativity, and that's what we can use to keep solving the problems that we're faced with.
And we do understand it, by which I mean the few people that still embrace progress. But the phenomenal thing for me is that this would just be a fun conversation to have in the abstract sense, if only there weren't prophets and pessimists heading up supranational institutions from the UN to the WEF to heads of government everywhere who have hitched their wagon to sustainability and to environmentalism, and to blame the ills of the world. They think they've identified the most serious problems that are out there, and the only way of solving these serious problems that are out there are to control the population in some way to reduce the amount of energy and resources that are being used, for fear that more and more irreversible damage will be caused to the world. And this impulse, in order to, what they would say is to help out of compassion the most impoverished denizens of the world, to ensure they aren't the primary victims of, let's say, climate change, has precisely the opposite effect, because it reduces our capacity to innovate and to create wealth throughout the world. And so it's just a shame that, although many of us can see the obvious flaws in these arguments about how protecting the planet at the cost of people is precisely the wrong thing to do if what you want to do is to solve the most important problems of our time, as people say.
Well, the thing I notice about discussions about climate change is that it's very often people are having a discussion about the wrong kind of thing, which is, discussions about actual climate science are not controversial. And the discussions about what we should do in response to those findings are not clear. So economics of climate change are not clear, but the climate science is. And usually what people focus on is the climate science, but that leaves aside that there is actually, you can have a very detailed and in-depth discussion about what should happen with the economic side of things. And it's also the side where people are most prone to actually dismiss the experts. I mean, typically people say that the experts are being dismissed on climate science, which is true, but then when we have to calculate the actual, when we have to figure out the actual economic solutions, these same people are dismissing the economists and dismissing things like geoengineering as being completely unviable. And it's weirdly paradoxical. I always find these discussions very strange because these people are assuming that we are changing the climate by accident, but that we cannot change it intentionally and for the better.
Yes.
That, yeah,
it's reminiscent to me of the discussion around seismology. There's no real debate about the extent to which the movement of tectonic plates causes earthquakes. In the same way that climate science, if the climate physicists are telling us, well, this is the way in which carbon dioxide causes the trapping of heat and so on and so forth. But there's a big difference between saying, therefore, progress needs to halt so that we don't exacerbate the problem. In the same way that in California, they don't say, well, seismology tells us that, the earthquake is going to happen in and around Los Angeles and San Francisco, so therefore we shouldn't be building anything more. No, the opposite is true. They double down and they make buildings more robust and they learn to live with the problem that they've identified in some way, shape or form. And I think the lesson there for climate science is similar. Yes, you might want to mitigate the amount of damage that you are doing, but in the meantime, prepare for what you've identified as a scientific prediction coming out of a good explanation of how the climate is indeed changing. Whether it's caused by people or not caused by people, we know the climate will change and we should want to change the world in response so that we can live comfortably. As people in California learn to live with earthquakes, or people who live near volcanoes learn to live with volcanoes. The earth is not necessarily a friendly place. The earth is a home and we want to make it more habitable.
Yeah, to drag the Netherlands back into the conversation, I mean, it's a country that is, for the most part, below sea level, and that took adaptation and innovation, and literally no one has died of anything like flooding in ages. Like, that is a solved issue at the moment, and there's no reason why it couldn't be. There's a very nice guy whose name I now forget, he's Dutch and works for the UN, and sometimes goes to the US and tries to persuade people to build more dams and things. And at some point in an interview, he said something like, the disasters themselves are not necessarily avoidable, but any of their damage is completely avoidable. Like, we can avoid all damage from natural events. Natural disasters are not necessarily avoidable, but the damage caused by natural disasters are almost entirely avoidable, if not completely. And that's very true. It's and again, shown by the Netherlands, shown by lots of places that have adapted to their environment, and we should want to do that more. It's very strange that there are practical solutions out there for lots of these things. Yeah, it's often people seem to be saying that if we are just practical, realistic people, then we should really stop burning fossil fuels and stuff like that. But there are, building dams is as practical as it gets, I think. We can do that now.
Well, as David Deutsch has said, we're living in an age of hyperbole, and so if people think they've identified the end of the world as nigh, they'll keep on pushing that for the moment. But I think, Sam, thank you so much for your time. You've been extremely generous. Where can people find more about some of the ideas you've talked about today? What's your social media presence, and where perhaps might people find your papers on time? And are you writing a book on the Dutch Enlightenment at any point?
So they can find me on Twitter. I'm on Twitter, and I suppose that the handle or something will be included, but it's at Sam Kuypers. And I have a Substack. And a Twitter, and my papers are online, and I think yeah, anyone who Googles my name's in the papers, they should be able to find them. So yeah, those are the main places people can find me at the moment. And maybe at some point I am thinking about writing a longer post on Substack about the Dutch Enlightenment, which when it comes out you'll be the first to see.
Excellent. Well, thanks again so much, Sam. And, until next time, until I have more questions about time and associated ideas, I'll talk to you then.
Great, thanks so much for having me.